In this video, I'm going to go through the slides that were uploaded related to introduction to waves. And so there are these 5 learning outcomes here. Describe the motion of transverse and longitudinal waves. Describe waves in terms of their wavelength, amplitude, frequency, speed, and intensity. Determine the frequency of sound waves using a cathode-ray oscilloscope. State the wavelengths of the principal radiations of the electromagnetic spectrum. And calculate the properties of a wave generated from a moving source, the Doppler effect. All right, describe the motion of transverse and longitudinal waves. Remember that a wave could be thought of as a periodic disturbance traveling through space characterized by a vibrating medium. And a progressive wave is a wave that carries energy from one place to another. And really, we can distinguish that from a stationary wave or a standing wave as, a standing wave does not transfer energy from one place to another. All the energy is sort of within the wave. So this definition kind of makes more sense once we get to the chapter on stationary waves and say, okay, a progressive wave is a wave that carries energy from one place to another. If that progressive wave gets to a boundary and then it's reflected and then the return wave comes back and interferes, then the energy is no longer being sent, sort of like all the energy has been delivered, but we have energy sort of within that standing wave. So when you think about comparing and contrasting progressive wave with stationary waves, which I'll upload the slides to that, a video corresponding to the slides to that shortly hereafter. So here's a diagram that shows a transverse and a longitudinal wave. We can see here that the direction of energy propagation would be from left to right. So the energy is moving this way in both the longitudinal and the transverse wave. And the slinky particles here are moving at right angles in the transverse wave. And so each particle of the slinky, like that bit of slinky, this bit of slinky, they're moving not left and right, but up and down, right? And so if the particles are moving at right angles to the direction of energy transfer, then we call that a transverse wave. Here, the particles, the sort of like this particle of slinky right here is moving left and right. Here it happens to be in the middle of an expansion or a rarefaction. In the middle of a compression, right, we could see like here's a particle of a slinky. And so these slinky particles are moving left and right. And that is parallel to the direction that the energy is being transferred, right? Because the energy is also being transferred from left to right. Another thing that I'll sort of point out here, or that's pointed out down here, the wavelength is the distance from the middle of this compression to the middle of this compression, or from the middle of this expansion to the middle of this expansion. So we get to the definition on wavelength, we're looking for the sort of the adjacent exactly similar point, or we'll sort of take a look at the language on the slide for that. So that's the key idea with transverse and longitudinal waves. See the link to the video there. Here's a good textbook definition to have in mind when you're thinking about transverse and longitudinal waves. And so the definitions, the explanations I just gave, you can see spelled out in words here. Sound is a longitudinal wave, and so sound is like a pressure wave. Pressure is force per area, and so as particles clump up, they're crashing into sort of other air particles, and so we're getting this transfer of energy along the direction of energy propagation. So you see the speaker there, and it's pushing air particles, and that sort of creates a pressure wave where all those particles are going to crash into other air particles, and we see those points of or those places of compression and those places of rarefaction. Rarefaction. That's a tough word to say. Expansion. Here's another diagram kind of showing the same thing. Because it's so difficult to illustrate a longitudinal wave and sort of how these particles are moving, sometimes we'll show the waveform, just sort of using this kind of waveform down here, even though we know it's a longitudinal wave. So be aware of that. We have to kind of know that sound is a longitudinal wave, even though sometimes in some problems it may be represented as like a transverse wave like this. These are some just definitions related to describing waves in terms of their wavelength, amplitude, frequency, speed, and intensity. I'll go through them very briefly. The distance from any point on a wave to the next exactly similar point, like crest to crest, is called the wavelength. The distance of a point on the wave from its undisturbed position or equilibrium position is called the displacement, and sometimes we'll call that x. The maximum displacement of any point on the wave from its undisturbed position is called the amplitude A. The time taken for one complete oscillation of a point in a wave is called the period t. The number of oscillations per unit time of a point in a wave is called its frequency f. And then velocity v is equal to the wavelength times the frequency. The period t is equal to 1 over the frequency, and the frequency is equal to 1 over the period. So the period and the frequency are inversely related. And source of waves is a disturbance. The greater the disturbance, the greater the amplitude. Intensity is proportional to amplitude squared. Intensity is the power per area. And so how much power per area is related to the amplitude, the amount of disturbance in the wave. And so if we think about like a water wave, if you push down, on water a lot more, you're displacing it a lot more. It requires more energy to do that. And therefore that energy will be contained within the wave, and that wave is going to transfer that energy like a progressive wave does. It really is helpful to discuss the vocabulary, to just kind of talk through the ideas. And even though it seems redundant, this is something that those of you that have me in class know that I do this a lot, where I'll just sort of be very redundant with the vocabulary, and that's just to reinforce it, because having the definitions in mind is sort of the first step to being able to get to more interesting and complicated ideas. And that's kind of what these slides are about here, just describing waves in terms of their wavelength, amplitude, frequency, speed, and intensity. And so some of the same definitions that you saw in the previous slide are here again. So I think that's just the same information. All right. Let's try to see what helpful information we can glean from a slide like this. So right away we see here's a crest defined and a trough defined. Sort of pointed out right here. The wavelength they've got from crest to crest, but it could also be from trough to trough. We can see that those distances are the same as long as the wave, has a consistent wavelength. It doesn't change its frequency over time or something. Which we can, modulate the frequency of waves. All right. If you've ever listened to FM radio, that FM is a frequency modulation, so we can sort of encode information in changing a frequency or an amplitude. That's AM radio. We modulate the amplitude of the wave. Here they've sort of blocked off 1 second of time. They're saying, this much space on the screen represents 1 second of time. It's kind of like the cathode-ray oscilloscope objective. That's kind of what a cathode-ray oscilloscope does. It allows us to visualize time. So here we see one waveform from the trough here to the trough here, and it occupies, or it took 1 second of time to propagate, and so that would have a frequency of 1 hertz, 1 wave per second, so 1 hertz. Here, though, we see that there's our wave, but then we get another like half of a wave, and so 1.5 waves per second. Okay, so we're counting the number of waves per unit time, and that's how we're getting this frequency over here, 1.5 hertz. That's 1.5 waves per second. Hertz is the same thing as the unit's reciprocal seconds, which we could write like seconds to the -1, right? So reciprocal seconds, the seconds are in the denominator. Or you think about like 1 over seconds. All right. So those are all sort of equivalent ways to think about the units there. Let's take a look at this example now. So here we can see we've got, there's 1 wave, 2 waves, 3 waves, right? 1, 2, 3, and maybe a half. Kind of just rounded it there. I'm making a mistake here, so we go from this point to that point to that point, so that's 3 waves. We get another like quarter of a wave, maybe, half a wave or so. 3.5 waves per second, or 3.5 hertz. They rounded it down to 3 there. I kind of see a little bit more than 3 waves there. You can use your own judgment and decide. This is kind of showing that inverse relationship too between period and frequency. If we were to think about the period, right, if this is The period is the amount of time it takes for one wave to propagate. And so here we could see that on, this higher frequency, this 3 or 3.5 hertz wave down here. Well, maybe it does start a little bit lower, right? So let's be more careful. All right, let's try it again. So when does the wave repeat? It repeats like right here, right? Down there. So that's one wave. That's two waves. That's three waves right there, right? Like the wave starts right here. So yeah, I mean, there's no way around it. That's like 3.5 or so waves per second. All right. But anyway, we were talking about frequency is 1 over the period, and the period is 1 over the frequency. And so, mathematically, you could say, well, if I know the frequency, like what's 1 divided by 3.5? Can we do that in our head? 0.2857. So they're saying, one of these waves right here, all right, that guy right there, that would have a time period of 0.2857 seconds, right? So if there's 3.5 waves per second, then each wave is taking 0.2857 seconds to propagate. So you'd have 0.2857, another 0.2857, another 0.2857, and then another half of that, and that would be, your total 3.5, right? So or your total 1 second rather, right? This amount of time is 1 second. So if there's 3.5 waves per second, then each one of these is, 0.2857. So it's helpful to kind of, play around with the numbers and to really not just passively watch this video and say, okay, that all makes sense, but actually write it down on paper and, include it in your notes and make sure that these ideas are making sense. If you have any questions about any of it, please don't hesitate to either leave a comment down below or, if you're one of my students, send me an email. All right, here they've left the y-axis as like a mystery, and but we could say that that's displacement, all right? And so the maximum displacement is the distance from equilibrium, sort of like this undisturbed position here that we can call, a displacement of 0. We'll just call this d for displacement, not to confuse it with this distance down here. So the displacement is how much each particle of the medium is being displaced as the wave propagates, and that wave is transferring energy, right? And so it's transferring it over a distance, and that's what they're plotting, on this top graph here. The slide is really designed to illustrate how we can sort of look at different features of a wave graphically. We could look at distance, and we'd be able to read things off like wavelength, like we see on this top one, right? So we've already kind of talked about from crest to crest, that's the wavelength. Well, if we're plotting distance, then we could, maybe quantify that. We could measure it. But if we're plotting time, then when we look at the amount of space occupied on a wave from crest to crest, it's not the distance, it is the time period of the wave. So how much time it takes the wave to oscillate. So just be mindful of that, sort of what are we looking at on the x-axis, and then here we'd still be sort of looking at the displacement. How the bottom graph here is sort of more a function. How is the displacement of the particles changing as a function of time? So let's recall the definition of period. It's the time it takes to complete one vibration or oscillation or cycle. And the definition of wavelength is the distance of a wave that a wave travels in one complete vibration or oscillation or cycle. So like the wave is the energy that's being transferred through the medium, right? So the wave kind of is the distance that wave travels. The particles sort of remaining in place are going to sort of, let's say it's a transverse wave, and so it's a water wave moving past. Well, the water is all undisturbed, and as that wave moves through, then the particles, oscillate at right angles to that direction of energy transfer. But the distance that wave traveled in one complete oscillation, that's the wavelength. The time it took the wave to do that is the time period. All right, so this was a lab day that we had, and it was to download an oscilloscope app. And so if you have means to do that, you can just, look up free oscilloscope apps, play around with that. Pretty cool. It will help. It will immensely help you understand this idea of being able to determine, frequencies using cathode ray oscilloscopes if you work with the technology a little bit. And so your your smartphone is not using cathode rays, but is an equally acceptable oscilloscope. This slide on the Doppler effect is kind of designed to show a little bit schematically where sort of these equations come from. I'll sort of briefly explain this, and I plan on sort of making another entire video sort of dedicated to this. And so I'll just briefly say that you can see this ambulance down here, and because it's moving, sort of it's catching up to the sound waves that it's already put out. And so see how this sort of outer, each one of these is a circle. Okay, maybe the shape looks a little bit skewed because of the sort of how they're clumping up on the side. But if you were to sort of just look at each one of these, it's a perfect circle. All right, and so each circle sort of represents the sound waves that have been put out by this ambulance here. If the ambulance is just stationary, then all observers all around it are going to hear sort of an equal frequency because the waves are arriving to that observer, in equal time. But if we look at this observer here, there's got to be a way to set that one as the default, right? All right, this observer over here that the ambulance is speeding towards, you can see that the ambulance is like catching up to the sound waves that it's already put out. And so this sort of outer circle represents let's just say the first sound wave that, as soon as the ambulance turned on its siren, when the ambulance was here, okay, when it was still at this position, remember it's moving, right? So when the ambulance was in the center of, that outer circle, it put out this sound wave. Well, by the time that the ambulance makes it to this point, okay, it's still been putting out sound waves all the while. It's getting closer to that sort of where that first sound wave has made it, right? It's speeding away from that sound wave that it put out in the opposite direction. So the sound waves are propagating, in all directions equally. And because it's moving in one direction and continuously putting out those sound waves, it's catching up to the sound waves it's already put out. You can kind of see that over here. That effectively means that the wavelength is getting squashed. Okay, so it's getting shorter and shorter. It's catching up to the sound waves it's already put out. So a short while later, like let's just say here's like the next moment, that we're sort of looking at, it put out this sound wave right here. Right? Well, it hasn't had so long to go as the first one, and so it hasn't made it as far yet, and so it's only sort of made it to here. And likewise this one, and so each one of these sort of perfect circles here just represents how far the wave has made it. Right? And each moment you're drawing that circle a little bit further over to the right because that's where the ambulance is by that point, right? It's putting out those waves just from wherever it is. And so it's important to remember that the Doppler effect is an apparent frequency. So it's based on the relative motion of an observer and a moving source. And let's just use this example of sound waves here, but the Doppler effect works for all types of waves, including light waves. And that's really fundamental to astronomy. Sign up for astronomy if you're interested. We sort of use the Doppler effect in redshift to make sense of the universe. So understanding this idea that was actually first experimentally verified, not by Doppler, but what was the gentleman's name? A very, very interesting name. Again, I plan on making an entire sort of video dedicated to the Doppler effect, and so I'll upload it there. But it was, first verified with like trumpet players on railroad cars and things like that. Play a consistent note, and as the railroad car sped away, you could observe this shift in the frequency. So it's an apparent shift in the frequency of a wave due to the relative motion of an observer and the source of the wave. And it could be either the observer is speeding away or towards the source of the wave, or the source of the wave is speeding towards or away from the observer, or maybe both are happening. And the equations that are very tough to read, up here, sort of capture how we could calculate how that frequency, changes. If you take a look at the many worked examples that I've done, you'll be able to see that equation. I'll leave it to you to click on the link there for that. There's the equation for the Doppler effect. So the frequency of the source times the velocity of the wave divided by the velocity of the wave, and then plus or minus the velocity of the source. So remember, it's an apparent shift in frequency due to the relative motion of an observer and the source of the wave. And so if the source is moving towards the observer, then we would subtract in the denominator here. But if the source were moving away from the observer, then we would add. And that would effectively make it so that when a source speeds away from an observer, you would hear it at a lower frequency. Right? Frequency gets lower. Meow, right? So that sound of a car engine passing by is a result of the Doppler effect. I think I've included that on at least one other Doppler effect worked example. I'll leave it to you to find that one. All right, what would a calculation look like in terms of this Doppler effect stuff? State what is meant by the Doppler effect. Doppler effect, again, it's an apparent change in frequency due to the relative motion of an observer and the source of the wave. An apparent shift in the frequency of a wave. Make sure you include that in your definition. An apparent change in the frequency of a wave due to the relative motion of the source of the wave and the observer. There you go. A source of sound of frequency 875 hertz moved toward a stationary observer at a speed of 35 meters per second. The speed of sound is 330 meters per second. What is the frequency of sound heard by the observer? Well, this gives us a chance to really kind of work through that question. So we want to solve for the frequency heard by the observer. Because it's moving toward, that means we're going to do what? Do we add or do we subtract? Pop quiz. Correct. We're going to subtract when the relative motion is such that they're moving towards each other. So the frequency of the source, the frequency observed is equal to the frequency of the source, which they tell us is 875 hertz. Now, because all the units are already meters per second, per seconds, hertz, we know that we're going to get a frequency out in hertz. I'm just going to kind of write the numbers in here. So this would be the frequency of the source multiplied by the speed of the wave, because it's a sound wave in air, 330 meters per second. So that will give us our numerator, the product of those two, divided by the velocity of the wave, which is 330. And because we were so successful in our pop quiz, we know we have to subtract away the 35 meters per second. Can you do that in your head? Or do we need a calculator check? Everybody that tried the sample calculation as you went through your notes and got 979. So my calculator value is like 978.8. Let's think about significance here. Probably two significant digits. And so the best answer for this would be 980. So at 875 hertz is going to sound higher pitched, right as it speeds toward. That's higher pitched than is lower pitch. So it's going to, its frequency would appear to be 978.8, but when we think about how precisely we can report our answer, and it's always a good practice, even though we've kind of cleaned up our calculation over here and we didn't include units, it's always important to make sure first that we can do that, that there is no kilometers, in there or anything that we have to convert first. Once we've kind of looked and said, oh, it's a friendly question, they've given us all the nice, SI units, no conversions needed. Let's just substitute in the values here into our equation and then solve it. But you should always put the units back in when you're reporting a final answer there. So we're mindful of significance. We've included our answer. The frequency observed would be 980 hertz. Good work example. Determine the frequency of sound waves using a cathode ray oscilloscope. There are many worked example calculations that I've uploaded. You can take a look at the link there. Because I'm going through an explanation here, I do want to briefly explain sort of what's going on. A cathode ray oscilloscope is a way to sort of convert the input signal into, something that we can visualize. And so we have a microphone, let's say, for sound waves, then as the microphone is converting those pressure variations, so as the air particles are moving, the microphone is sort of converting that into an electrical signal, that motion into an electrical signal. The amplitude of the wave, we already know, is proportional to how much energy is in the wave, right? The intensity is proportional to the amplitude squared. And so we're going to get a larger signal if it's a louder sound. And so we could scale the vertical axis with this, and you can see volts per division, and we would be able to sort of do a calculation and say, well, how much voltage that we're reading off on the y-axis is related to the energy in the wave. The time-based setting is typically where we spend most of our time kind of looking at calculations, although there are questions that involve the vertical axis too, and it's just important to remember our definitions of amplitude and how that relates to energy and so on. But for the time-based setting, you can maybe see, if you've got really good eyes, that it's seconds per division. So it's telling us how much time each one of these divisions represents. And you can see that there's a dial there that we'd be able to adjust sort of how much time each division represents, because we might be looking at waves that are, very, very short period, very, very long period. And so we might need to adjust it into the milliseconds or microseconds, or maybe not. And so here I think they've got it set to 16 divisions, so 1 millisecond per division. Each one of these divisions is a millisecond. That's what they would have the time-based, setting set to. And the way that we do the calculations here is we're always trying to sort of visualize an entire waveform on the oscilloscope. And let's just say you put a signal into your oscilloscope and you can't, all the waves are so crunched up you can't hardly even see it. Well, you need to adjust the time-based setting in order to sort of spread the wave out so that you can cleanly and clearly see, oh, there's a waveform, how many divisions, and then you could do your calculations. So you're always trying to get sort of like a clean number of waves inside of your scope there, right? The sort of part that you can see in the oscilloscope. So they've counted out that there are 16 divisions, okay, to get to one wave. And so they're looking at kind of like this point of the wave right here to this point over here, and they've counted out there are 16 of these divisions. And if you want to, you could sort of verify that for yourself. I trust it. 16 divisions at 1 millisecond per division. So as a period of 16 milliseconds, right? So each one of these is a millisecond. So they're saying 1 millisecond, 2 milliseconds, until they get over to 16 milliseconds. Because we already know that frequency is 1 over the period, then you could just do 1 divided by 16 milliseconds, and they get this frequency over here, which I guess is 62.5 hertz. Let me verify that in my calculator. So 1 divided by 16, and then milli is 10 to the negative 3, and so that's 62.5 hertz. And so there's an example of, if you see a wave like that, and you know the time-based setting is 1 millisecond per division, one strategy is to just count off the period. Then you'll know T is 16 milliseconds. That's the time it took this one wave to oscillate, 16 milliseconds. You could take the inverse of that to get the frequency. If you take a look at the worked examples that I've done, I've shown different ways to sort of think about these calculations. It's important to work with the ideas enough that you're very familiar with sort of any way to attack the question. It usually kind of depends on what are they asking for, what are you given, what's the most elegant path to the solution, the most time efficient path. Here's just sort of a schematic showing that. So here's our vibrating loudspeaker, and we can see that here the showing us the wavelength, right? From this compression to this compression, the microphone is picking up that, and we're getting a signal in our oscilloscope here. You can read off the time period, right? So we're always kind of getting the period of the wave to get the frequency. It's the inverse of that. Another worked example here. They're telling us one full wave occupies 6 squares, and so if they go from this point over to maybe that point right there, we got 1, 2, 3, 4, 5, 6 divisions, and each division is 0.02 seconds, so the period is 0.12 seconds, right? Just counting from 0.02, 0.04, and so on until you get this, and then do the inverse, 1 divided by the period, so this wave here would have a frequency of 8.3 hertz. This slide here is connected to the learning outcome, being able to sort of state the principal wavelengths of the EM spectrum. So here you see the electromagnetic spectrum, all the different sort of types of light. Light exists on a spectrum, and we can see one tiny sliver of that spectrum, the visible part of the spectrum. And this slide also is showing kind of like what radiation makes it down here to Earth's surface. I want to take a moment here to discuss, kind of briefly, the idea of penetrating power and ionizing radiation. So in the radioactivity slides, we talked about alpha, beta, and gamma decay. And here we see like gamma waves. And note that they don't make it all the way down to Earth's surface, and that's a good thing. So any gamma radiation that's incident upon the Earth's surface is I mean, even though gamma radiation is weakly ionizing, as it enters Earth's surface, it's going to ionize some of the particles that it's passing by and lose energy, and so it doesn't make it all the way down to Earth's surface there, and that's sort of connected back to the radioactivity chapter. It's crucial that you all connect ideas and see, how do the waves physics connect to radioactivity? Well, one obvious way is with gamma, radiation, right? Because it's a type of radiation that we study in radioactivity, and it's a type of light that we study. We study waves there. So there's sort of one obvious way, but there are many other ways that these ideas are connected, and that's really at the heart of physics, is being able to work through an idea that is very broadly applicable, to work it out as simply as possible, but as Einstein would say, not more simply than that. So the remaining slides here, I think, are focusing on the electromagnetic spectrum, and there's sort of different ways to think about this. I think this maybe comes from like solar saunas, and so the infrared part of the spectrum is really important, to make solar saunas or something. This slide kind of allows us to see wavelengths on a scale that maybe we're more familiar with. So like radio waves, the size of houses or soccer fields. This period right here, infrared, the size of cells, bacteria, proteins, water molecules, and so on. And you will have questions. I'll say, state what wavelength of light is about the same size as a water molecule, and there you'd kind of look at the X-ray sort of part of the spectrum. There is an overlap between gamma radiation and X-rays. It's sort of where is that light created? So when we decelerate electrons and create X-rays, or create light with that frequency, it's an X-ray. But gamma radiation comes from radioactive nuclear processes. There's this mnemonic device. Rowdy Martians invade Venus using X-ray guns in order to memorize sort of the order: radio, microwave, infrared, visible, ultraviolet, X-ray, gamma. And then for ACE physics, it's important to know what these values are. And there was a really good vocabulary review video where all of those wavelengths are mentioned there. I'll leave it to you to take a look at that. And so this is definitely something that should be in your notes, something that, and here they're all listed in meters, and that's the same way that sort of the vocabulary review was structured. But it's also helpful to think about it kind of the way that the slide up here does. And so we say, well, this is kind of like, centimeters, so where are we if we're at, like, centimeters? That's 10 to the negative 2 meters. And so microwaves are, centimeters long. And so using the metric prefixes not only helps familiarize you with that, which is, we're somewhat unfamiliar with, but it might be another approach to help reinforce just the kind of strict memorization of, hey, these are things that I need to know for certain questions, especially in ACE physics. And then this last slide here is just a figure showing electromagnetic radiation. And so we have here is an electric field in one direction and a magnetic field perpendicular to it. And that's really what light is. And the discovery of light as an electromagnetic phenomenon is one of the most important in all of physics. And I'll save that for another video to talk more about this discovery of light as an electromagnetic phenomenon.